So, hello everyone, I'm András Retzler and I'm a PhD student. I'm going to talk about shooting methods for identification of nonlinear state space gray box models. And so in this research, our goal was to estimate the parameters of gray box models, models that we can express with a set of differential equations that depend on a set of parameters, and specifically models of systems with inherent nonlinearities. So the comparison, that's the main contribution of our work, is of different methods of shooting type with respect to robustness against initial parameters in a non-contractive region. I will explain that later, and also on running time. And the comparison has been carried out on a nonlinear system called EMPS that's going to be described in the next few slides. And so we used both our own toolbox and the system identification toolbox of MATLAB. So the system considered is called electromechanical positioning system, and the data set and the model and the related publication you can find as seen on the bottom of the slide. The model looks like this. So the red ones are the parameters to estimate. There are 4 of them, like the M, the FV, FC, and the C, which are M is related to inertia, FV and FC are about friction, and the big C is an offset. And there are different methods for identifying the EMPS. The first one called inverse dynamic identification model with least squares estimation, that's described in the original paper, with which the dataset was published. So this one will not work in all cases, like it will not work with all kinds of models, only if that part in the model is in the OD is linear in the dynamic coefficients, the so-called dynamic coefficients or barycentric parameters. But we have changed the formula to achieve a bit lower relative error on their validation dataset. So we changed the friction part, and then with the new formula it would not work, the original method. So then we go with shooting methods. And yes, there's the single shooting formulation. It's basically, in the objective we can see a free run simulation of the states, starting from an initial state, and so that involves recursion, because every time the state is calculated based on the previous state. And that's a problem, because then it might be that we have very big numbers in our matrix after we do the simulation. So that's what I mean when I say that the model is non-contractive for given values of decision variables. So if you look at the parameter space, you see that there are ranges where this happens, and if our initial value for the decision variables lies there, then the optimal parameter values lie there, then it might be that the solver is taking steps, but then it's just at one point it walks into this region where the simulation is just blowing up numerically, and we get some kind of error message that's concerning nonce in the matrices. And also if we start from this kind of region, then we get an error message right away. So we cannot even start the optimization, and this is the main problem that we see here. Another problem is that the objective in case of single shooting it's non-convex, and also it's not smooth. Or I can say there are other formulations where it's smoother. But it's very easy to go into local minimums that are not the best local minimum. When I talk about robustness, then it's robustness against these kind of problems. So let's take a look at the other formulations. The multiple shooting formulation is computationally heavier because of the constraints and the new decision variables that are there in the formula. And on the other hand, it's able to pass previously non-contractive parameter ranges because we don't have recursion there at all, and the objective is still non-convex, but it's smoother. And there's a formulation called partially constrained multiple shooting where the recursion depth can be controlled, so it allows us to find a compromise between robustness and computational complexity. The fourth formulation is based on that. For electromechanical systems, we can many times we can just measure some of the states, like the positions, and infer the other states. Like the velocities are just a derivative of the positions. If we do this with finite differences, then this will not be very accurate. But if it's a possibility, that we can measure and or infer all the states, then we can use this information in the following ways. We can use it either as initial values for decision variables in multiple shooting type formulations. So we can also minimize a one step ahead prediction error starting from the previous states fixed to these values that we measured or inferred. And this formulation is the one that I call PEM. So the pro of PEM is that it's a simple problem, usually fast to solve. The drawback is that it only works if we can measure or infer all the states, and the resulting model will not be very accurate in simulation. So that what we can do, we have then run single shooting starting from the parameters that we acquired using PEM to refine the model accuracy. So then with respect to single shooting, it's in the system identification toolbox that's in MATLAB, and to our understanding, MATLAB only supports that kind of formulation. So when you call the nLGray-est function, then that formulation is executed. Our toolbox, in our toolbox, we have implemented all the other formulations shown here as well. And so yeah, this is our toolbox. This is open source. For optimization, we are using a toolbox called Casari that's also developed in our group. So what have we done for the comparison? We have generated 100 different multicyclic citations, and we simulated the system output for these, and we checked so we tried both nLGray-fast and nLGray-est to calculate the parameters that we used during simulation. So for the comparison with respect to robustness, in the estimation we used initial parameter values that are in a non-contractive or a contractive region. So we tried both cases, and so one of the ways we have evaluated this is that we checked how many cases out of the 100 was the relative error of the simulation, which is like the relative error between the simulated and measured output. for the parameters that we acquired using system identification. So in how many cases is it lower than a threshold, and yeah, we tried with different methods. You can see there the single shooting, the multiple shooting type, and the PAM type methods. And what we can see is that the multiple shooting type methods cannot solve all the cases. On the other hand, PAM alone is not very robust unless combined with single shooting. If we combine it with single shooting, then it solves in all cases, even if we start from a non-contractive region in the parameter space. And it has competitive relative errors, and the running times, with respect to running times, it's also the second best, the first being PAM, which is not accurate. So it's better than the multiple shooting type methods. So even though PAM plus SS was the most robust against an unstable initialization, we have to remember that, so we have to be able to measure infer all the states. So then another comparison we have made is on single shooting formulation. So the NLGray fast and NLGray est, like our toolbox and that of MATLAB compared, and we see here that the NLGray fast toolbox of ours is able to provide good solutions within like a magnitude lower time. But that's a thing that only counts in cases when we want to do online estimation, like combining system identification with MPC and such. As a summary, we have here the PAM plus SS, which is the most robust against unstable initialization, and the multiple shooting type methods were also working but not as robust. And the single shooting was not working at all if the initialization point was unstable for the EMBS system. Also in all experiments we used that we could measure or infer all the states. Thank you for your attention. You can find the link to our toolbox on the slide, and let me know if you have any questions.